Welcome to our soothing exploration of the chemistry behind one of nature's most breathtaking phenomena, the Aurora Borealis. As we embark on this tranquil journey, we will delve into the scientific intricacies that illuminate the night sky with vibrant colors. The Aurora Borealis, also known as the Northern Lights, is a stunning display created by the interaction of charged particles from the sun with molecules in our atmosphere. In this calming presentation, we will explore various aspects of this enchanting spectacle, gently guiding you through the science that underlies its beauty. Allow the peaceful cadence of our discussion to relax your mind and ease you into a restful state as we uncover the chemistry that creates these ethereal lights. To truly appreciate the Aurora Borealis, we must first understand its fundamental nature. The Aurora Borealis is not merely a visual delight. It is a complex interplay of solar activity and atmospheric chemistry. This mesmerizing phenomenon occurs when charged particles, primarily electrons and protons, emitted by the sun, collide with gases in the Earth's atmosphere. The result of these interactions produces the vibrant colors that dance across the polar skies. At the heart of this phenomenon is the solar wind, a constant stream of charged particles released from the sun's outer layers. These particles travel through space at astonishing speeds, often exceeding 400 kilometers per second. As they journey towards Earth, they encounter the planet's magnetic field, which acts as a protective shield. This interaction is crucial, as it determines how and where the charged particles will enter the atmosphere, leading to the stunning displays we associate with the Northern Lights. As we move deeper into the chemistry of the Aurora Borealis, we must explore the specific role that solar winds play in this process. The solar wind is composed mainly of electrons and protons, but it also contains heavier ions, such as helium and oxygen. When these charged particles reach the Earth, they can be guided by the magnetic field lines towards the polar regions. This is why the Aurora Borealis is predominantly visible in areas close to the magnetic poles, such as Alaska, Canada, and Scandinavia. When solar winds collide with atmospheric gases, they impart energy to these gas molecules. This energy transfer is a key aspect of the chemistry involved in the creation of the Aurora Borealis. The gases in our atmosphere, primarily nitrogen and oxygen, absorb this energy, causing their electrons to become excited. Excited electrons are in a higher energy state, and when they return to their original state, they release energy in the form of light. This phenomenon is known as light emission, and it is responsible for the beautiful colors we observe in the night sky. The basic principles of atmospheric chemistry involved in the Aurora Borealis can be understood through the concept of ionization. When a charged particle from the solar wind collides with an atmospheric gas, it can strip away electrons from the gas molecules. This process creates positively charged ions and free electrons, leading to a cascade of further reactions. As more and more particles interact, they create a vibrant display of colors, depending on the type of gas involved and the altitude at which the interactions occur. For instance, when solar particles collide with oxygen molecules at higher altitudes, typically above 200 kilometers, they can produce a beautiful red or purple hue. Conversely, when these interactions happen at lower altitudes, around 100 kilometers, the result is often green or yellow light. This variation in color is a direct result of the different energy levels associated with various gases and their unique responses to ionization. Now, let's delve deeper into the role of nitrogen in the chemistry of the Aurora Borealis. Nitrogen is the most abundant gas in the atmosphere, and it plays a significant role in the creation of the stunning displays we observe. When nitrogen molecules are excited by the energy transferred from solar particles, they can emit light in the blue or purple spectrum. The interplay between nitrogen and oxygen is what creates the multicolored tapestry that characterizes the northern lights. The altitude at which these interactions occur also significantly influences the colors of the aurora. As we have mentioned, higher altitudes tend to produce reds and purples due to the presence of oxygen, while lower altitudes yield greens and yellows due to nitrogen. This vertical gradient of colors adds depth and complexity to the auroral displays, making each sighting a unique experience. In addition to the specific gases involved, the intensity of the aurora can vary based on solar activity. During periods of heightened solar activity, such as solar flares or coronal mass ejections, more charged particles are released into the solar wind. This increase in particle density can lead to more intense and widespread auroral displays, with colors appearing more vivid and dynamic. As we explore the chemistry of the Aurora Borealis, it is also important to consider the atmospheric conditions that can affect visibility. Clear, dark skies away from light pollution are ideal for observing the northern lights. The presence of clouds, humidity, and other weather conditions can obscure the view, making the experience of witnessing an aurora even more precious. Each sighting is a reminder of the delicate balance between solar activity and atmospheric chemistry that creates this breathtaking phenomenon. The chemistry behind the Aurora Borealis is a beautiful example of how interconnected our universe is. The sun, with its powerful solar winds, interacts with the Earth's atmosphere in a way that produces a visual spectacle unlike any other. This delicate dance between solar particles and atmospheric gases is a testament to the complex systems at play in our world. As we continue our exploration, we will delve deeper into the specifics of solar winds and their composition, enhancing our understanding of this captivating phenomenon. The solar wind is not just a singular flow of particles, it is a dynamic and varied stream influenced by solar activity. The sun undergoes an 11-year cycle of solar activity, characterized by periods of high and low sunspot activity. During the peak of this cycle, known as solar maximum, the sun emits a greater number of charged particles, leading to enhanced solar wind conditions. This increased activity can result in more frequent and intense auroras, captivating observers across the globe. As we reflect on the beauty and complexity of the Aurora Borealis, it is essential to appreciate the role of scientific inquiry in uncovering the mysteries of this phenomenon. The study of auroras has evolved over the centuries, from ancient interpretations steeped in mythology to modern scientific investigations that employ advanced technology and research methods. This journey of understanding is ongoing, as researchers continue to explore the intricate connections between solar activity, atmospheric chemistry, and the stunning displays of light that grace our skies. As we approach the conclusion of this section, let us take a moment to appreciate the serene beauty of the Aurora Borealis. The colors that ripple across the night sky are not merely a visual delight, they are a manifestation of the natural laws that govern our universe. The chemistry that underlies this phenomenon reflects the delicate balance of forces at play, reminding us of our connection to the cosmos. In our next section, we will delve deeper into the composition of solar winds, exploring what they consist of and how they travel through space. We will further unravel the mysteries of the Aurora Borealis, enhancing our understanding of this captivating natural wonder. As we transition into this next phase of our exploration, let the soothing imagery of the northern lights linger in your thoughts, inviting you to dream of the wonders that await in the vast expanse of the universe. Rest easy, knowing that the beauty of science and nature is always within reach, illuminating our world with awe and inspiration. The Aurora Borealis is a breathtaking manifestation of nature's beauty, an ethereal dance of light that captivates the observer's imagination. To fully appreciate this phenomenon, it is essential to delve deeper into the composition and behavior of solar winds, the streams of charged particles emitted by the sun. Understanding solar wind provides a foundation for grasping how these particles interact with the Earth's atmosphere, leading to the vibrant displays we associate with the northern lights. Solar winds consist primarily of electrons and protons, both of which are charged particles. They originate from the sun's corona, the outer layer of the solar atmosphere, where temperatures soar to millions of degrees Celsius. At such high temperatures, particles gain enough energy to escape the sun's gravitational pull and travel through space. The solar wind flows outward in all directions, creating a continuous stream of charged particles that can travel at speeds ranging from 300 to 800 kilometers per second, depending on solar activity. As solar winds journey through the vastness of space, they can encounter various celestial bodies, including planets like Earth. Upon approaching our planet, the solar wind interacts with the Earth's magnetic field, a protective shield generated by the movement of molten iron in the outer core. This magnetic field extends far into space, forming the magnetosphere, which acts as a barrier against solar radiation and charged particles. When solar winds reach the magnetosphere, they can cause disturbances, particularly during periods of heightened solar activity, such as solar flares or coronal mass ejections. These disturbances can lead to an increase in the intensity of the solar wind, which in turn can result in more pronounced auroral displays. The interaction between the solar wind and the magnetosphere is a delicate balance. The magnetosphere deflects most of the solar wind, but during these intense events, some particles are funneled towards the poles, where they enter the atmosphere. As solar particles penetrate the magnetosphere, they collide with atmospheric gases, primarily nitrogen and oxygen. This interaction is crucial for the creation of the mesmerizing colors seen in the Aurora Borealis. The energy from these collisions excites the gas molecules, causing them to enter an excited state. When these molecules return to their normal state, they release energy in the form of light, a process known as emission. The specific colors produced in the aurora are determined by the type of gas that is excited and the altitude at which the collisions occur. For instance, when high-energy solar particles collide with oxygen at altitudes above 150 kilometers, they produce a vibrant red hue. Conversely, at lower altitudes, around 100 kilometers, oxygen can emit a bright green light, which is the most common color associated with the auroras. Nitrogen, on the other hand, contributes purples and blues to the palette, depending on the nature of the collisions and the energy involved. The complexity of these interactions illustrates the intricate chemistry at play in the formation of the Aurora Borealis. Each color is a reminder of the unique properties of the gases in our atmosphere and how they respond to energy inputs from the sun. The interplay of these elements creates a dazzling display, as the colours shift and blend, painting the night sky with ever-changing patterns. The altitude at which these interactions occur also plays a significant role in the appearance of the aurora. As solar particles descend into the atmosphere, they encounter varying densities of gases. At higher altitudes, the atmosphere is thinner, allowing for different colours to emerge. In contrast, lower altitudes present a denser environment, which can enhance certain colours while muting others. This stratification of the atmosphere contributes to the layered appearance of the aurora, often seen as curtains or waves of light cascading across the sky. Understanding solar winds and their composition is essential for unravelling the mystery of the Aurora Borealis. Solar winds are not merely a backdrop for the auroras, they are the driving force behind this natural spectacle. The sun's activity, such as sunspots and solar flares, directly influences the intensity and frequency of solar winds, which in turn affects the likelihood of auroras being visible on Earth. The study of solar winds and their effects on the Earth's atmosphere is a dynamic field of research, with scientists employing advanced technology to monitor solar activity and predict subsequent auroral displays. Satellites orbiting the Earth provide valuable data on solar wind speed, density, and magnetic field orientation, allowing researchers to create models that forecast auroras. This predictive capability enhances our understanding of not only the auroras, but also the broader implications of solar activity on Earth's environment. The chemistry involved in the formation of the Aurora Borealis is a testament to the interconnectedness of the solar system. The Sun, with its immense gravitational force and energy output, plays a pivotal role in shaping the atmospheric phenomena we witness on Earth. As we continue to study these interactions, we gain deeper insights into the fundamental processes that govern our natural world. As we immerse ourselves in the beauty of the Aurora Borealis, it is important to reflect on the scientific principles that underlie this phenomenon. The vibrant colours that dance across the night sky are not merely random displays, but are the result of intricate chemical processes and interactions. Each hue tells a story of energy transfer, of particles colliding and creating light, illuminating the darkness with their brilliance. The Aurora Borealis invites us to ponder the relationship between our planet and the cosmos. It serves as a reminder of the powerful forces at play in the universe. Forces that shape not only our environment, but also our understanding of science. The chemistry behind the auroras is a reflection of the intricate balance of nature, where even the smallest particles can have a profound impact on the world around us. As we conclude this section of our exploration into the chemistry of the Aurora Borealis, let us carry forward the knowledge of solar winds and their vital role in this phenomenon. The interplay of solar particles with atmospheric gases creates a mesmerizing display of light, a dance of chemistry that enchants observers across the globe. This understanding deepens our appreciation for the natural world and encourages us to look up at the night sky with wonder and curiosity. In the next section, we will delve into the ionization process of atmospheric gases that leads to the creation of the colors we see in the auroras. By exploring the specific gases involved, we will uncover how nitrogen and oxygen contribute to the spectacular visual display, further illuminating the chemistry behind this extraordinary phenomenon. As we transition into this next chapter, let the soothing thoughts of the Northern Lights guide you into a peaceful state of relaxation, embracing the beauty of nature and the science that explains it. As we continue our exploration of the captivating chemistry behind the Aurora Borealis, We now turn our attention to the fascinating process of ionization of atmospheric gases. This process is integral to understanding how the vibrant colors of the aurora are produced. When charged particles from the sun, carried by solar winds, reach the Earth's atmosphere, they encounter a multitude of gases. These gases, primarily oxygen and nitrogen, play a crucial role in the creation of the mesmerizing light displays we associate with the northern lights. To begin with, let's delve into the nature of solar particles. Solar winds are streams of charged particles, mainly electrons and protons, that are ejected from the sun's outer layer. As these particles travel through space, they can reach speeds of up to 1 million miles per hour. When these high-energy particles collide with the gases in our atmosphere, they impart energy to the atoms and molecules present. This interaction leads to the phenomenon known as ionization. Ionization occurs when an atom or molecule gains enough energy to lose one or more of its electrons. In the context of the Aurora Borealis, the ionization process is triggered by the energetic solar particles colliding with atmospheric gases at altitudes of around 80 to 600 kilometers above the Earth's surface. As these collisions take place, the energy from the solar particles excites the gaseous atoms, moving their electrons to higher energy levels. This state of excitation is temporary, and as the excited electrons return to their original lower energy states, they release energy in the form of light. This is the fundamental mechanism that produces the stunning colors of the aurora. The specific gases involved in the ionization process significantly influence the colors emitted during an auroral display. Oxygen, for example, is responsible for producing some of the more common colors seen in auroras. At lower altitudes, where the density of atmospheric gases is greater, oxygen can emit a reddish hue. This occurs at altitudes of around 300 kilometers. Conversely, at higher altitudes, the same oxygen atoms can emit a green light, which is the most prevalent color seen in auroras. The green light is produced when the oxygen atoms are excited by solar particles and then return to their ground state, releasing energy at a wavelength that is perceived by our eyes as green. Nitrogen also plays a significant role in the color palette of the northern lights. When nitrogen molecules are excited, they can emit a blue or purple light. These colors can often be seen in conjunction with the green and red hues produced by oxygen. The interplay of these gases and their respective emissions creates a dynamic and ever-changing display of colors that dance across the night sky. As we observe an auroral display, we are witnessing the result of complex chemical interactions that occur in the upper atmosphere. The altitude at which these gases are ionized and emit light is crucial for the variation in colors observed during an auroral event. As previously mentioned, the density of the atmosphere decreases with altitude. Thus, the specific conditions at different heights lead to different types of emissions. For instance, when solar particles collide with nitrogen at lower altitudes, the resulting colors can appear more vivid and varied, often showcasing deep reds and purples. At higher altitudes, the interactions tend to produce greens and blues, creating a layered effect that adds to the visual complexity of the aurora. In addition to the altitude and the specific gases involved, the energy of the solar particles also affects the intensity and color of the aurora. During periods of heightened solar activity, such as solar flares or coronal mass ejections, more energetic particles are released. These events increase the likelihood of intense auroral displays. The higher energy of solar particles can lead to more significant ionization of atmospheric gases, resulting in brighter and more colorful auroras. This relationship between solar activity and auroral intensity highlights the interconnectedness of solar phenomena and atmospheric chemistry. Furthermore, the Earth's magnetic field plays a pivotal role in directing the flow of solar particles. As charged particles travel toward the Earth, they are guided by the magnetic field lines. This interaction causes the particles to spiral down along the magnetic field lines toward the polar regions, where they collide with atmospheric gases. This phenomenon explains why auroras are predominantly observed in regions close to the magnetic poles. The magnetic field essentially funnels the solar particles into specific areas, leading to the concentrated displays of light that we associate with the Aurora Borealis and its southern counterpart, the Aurora Australis. The beauty of the Aurora Borealis is not only a visual spectacle, but also a reminder of the intricate dance between solar winds and the Earth's atmosphere. The chemistry involved in the ionization of gases is a testament to the dynamic nature of our planet's environment and the cosmos. As we gaze upon the shimmering lights, we are witnessing a physical manifestation of complex scientific principles at work. The vibrant colors are not merely aesthetic. They are the result of energetic interactions that occur far above our heads, illuminating the night sky with their splendor. As we continue to unravel the mysteries of the Aurora Borealis, it is essential to appreciate the delicate balance of factors that contribute to this natural wonder. From the solar activity that sends charged particles hurtling toward Earth, to the atmospheric conditions that determine how these particles interact with gases, each element plays a significant role in crafting the enchanting displays we admire. The chemistry of the aurora serves as a reminder of the profound connections between our planet and the broader universe. In our next segment, we will delve deeper into the specifics of light emission from excited atoms and how different colors are produced by different gases. We will also explore the significance of altitude in these color variations, providing a more comprehensive understanding of the chemistry at play during an auroral event. This journey through the science of the Aurora Borealis offers not only a peaceful exploration of natural beauty, but also an opportunity to reflect on the wonders of the universe and our place within it. As we transition to this next phase of our exploration, let us take a moment to reflect on the intricate processes that unfold in the atmosphere above us. The Aurora Borealis is not merely a display. It is a convergence of cosmic energy and earthly chemistry. The light that paints the night sky is a celebration of the interactions that occur at the intersection of solar winds and atmospheric gases, a dance of particles that has captivated human imagination for centuries. As we prepare to delve into the specifics of light emission in the next section, let us carry with us the knowledge that the colors we see are not random, but rather a beautiful symphony of scientific principles. The chemistry of the aurora invites us to marvel at the elegance of nature and the wonders of scientific inquiry. With each passing moment, we inch closer to a deeper understanding of the forces that shape our world, and in doing so, we find tranquility in the knowledge that we are part of a grander design. Now, let us gently transition into our exploration of the light emission process, where we will uncover the secrets behind the vibrant colors of the Aurora Borealis. The journey continues as we illuminate the science that makes this natural wonder so extraordinary. As we embark on this next chapter, may the soothing rhythm of our discussion guide you into a state of relaxation and contemplation, allowing the beauty of the Aurora Borealis to linger in your thoughts, inspiring dreams filled with wonder and tranquility. As we gently continue our exploration of the Aurora Borealis, we will now delve into the colourful displays that emerge in the night sky. Specifically, we will examine the chemistry of light emission, which plays a crucial role in creating the stunning visual spectacle that captivates so many observers. The vibrant greens, reds, purples, and blues that dance across the polar skies are not merely random occurrences, but rather the result of intricate interactions at the atomic level. By understanding how these colours are produced, we can appreciate even more the beauty and complexity of this natural phenomenon. When charged particles from the solar wind collide with Earth's atmosphere, the energy released during these interactions leads to the excitation of various atmospheric gases. These gases, primarily nitrogen and oxygen, become energized as they absorb the kinetic energy from the incoming solar particles. As these atoms and molecules absorb energy, they are propelled into an excited state. This state is temporary, and as the excited atoms return to their ground state, they release energy in the form of light. This process is known as light emission, and is fundamental to the creation of the auroras. The specific colours seen in the auroras depend on the type of gas that is being excited and the altitude at which these interactions are taking place. At lower altitudes, where the atmosphere is denser, we primarily observe green and yellow hues. This is largely due to the excitation of oxygen molecules at altitudes of approximately 100 to 300 kilometers. When these molecules are energized, they emit light in the green spectrum, which is the most commonly observed color in auroral displays. The brightness of this green light is what often draws the gaze of those who witness the northern lights. As we ascend to higher altitudes, the chemistry changes, and so does the color palette of the auroras. At altitudes above 300 kilometers, the interactions with atomic oxygen can produce red light. This vibrant red hue is less common than green, but can be breathtaking when it appears. The red light emitted results from a different type of energy transition within the oxygen atoms, and it often adds a majestic quality to the auroral display, particularly when it occurs alongside the more common green light. Moreover, the presence of nitrogen also contributes to the striking colours of the auroras. When nitrogen molecules are excited by solar particles, they can emit light in shades of blue and purple. This occurs at various altitudes, particularly between 100 and 200 kilometers. The blue light emitted from nitrogen is often seen in the lower parts of the aurora, creating a beautiful contrast against the greens and reds produced by oxygen. Occasionally, the interplay of these different colors creates a multi-layered effect, enhancing the overall beauty of the spectacle. The altitude at which these reactions occur is significant not only for the colors produced, but also for the intensity of the light emitted. The higher the altitude, the thinner the atmosphere, which can affect how the light travels and is perceived by observers on the ground. Additionally, the density of the atmosphere can influence the scattering of light, leading to variations in how colors appear. This is why some nights may present a vivid display of colors, while others may seem more subdued. The specific conditions during a solar storm can also intensify the colors observed in the auroras. During periods of heightened solar activity, such as solar flares or coronal mass ejections, the influx of charged particles is significantly increased. This surge can lead to more frequent and intense auroral displays, often resulting in a broader range of colors and more dynamic movements in the sky. The interaction of these additional charged particles with the atmospheric gases can excite them to higher energy states, leading to more vivid and diverse light emissions. As we contemplate the chemistry behind these beautiful displays, it is essential to appreciate the role of Earth's magnetic field. The magnetic field acts as a protective barrier, guiding and funneling the solar particles toward the polar regions. This is why auroras are typically seen in the high latitude areas near the Arctic and Antarctic circles. The magnetic field lines converge at the poles, creating a natural pathway for these charged particles, which then collide with the atmospheric gases, giving rise to the radiant colors we admire. Additionally, the shape and structure of the auroras can be influenced by the dynamics of the solar wind and the magnetic field. Auroras can appear as arcs, bands, or waves, often morphing and shifting in response to the ever-changing conditions of the solar wind. These movements can create an ethereal quality, as if the lights themselves are alive, dancing across the sky in a mesmerizing ballet of color and light. Each display is unique, shaped by the interplay of solar activity, atmospheric conditions, and the Earth's magnetic field. The study of the chemistry behind the Aurora Borealis continues to evolve, as scientists strive to understand the nuances of these interactions more deeply. Advanced technologies, including satellites and ground-based observatories, allow researchers to monitor solar activity in real time and correlate it with auroral observations. This ongoing research not only enhances our understanding of the auroras, but also contributes to our broader knowledge of space weather and its effects on Earth's atmosphere. As we immerse ourselves in the wonders of the Aurora Borealis, it is important to recognize the cultural significance of these lights throughout history. Different cultures have interpreted the auroras in various ways, often weaving them into their myths and legends. For some indigenous peoples in the Arctic regions, the northern lights have been seen as the spirits of ancestors or as a bridge between the living and the deceased. These interpretations reflect a deep connection to the natural world and a reverence for the mysteries it holds. In modern times, the Aurora Borealis has become a symbol of beauty and wonder, attracting countless visitors to regions where the lights are visible. Photographers and nature enthusiasts travel far and wide to witness this breathtaking phenomenon, often sharing their experiences and images with the world. The allure of the auroras continues to inspire creativity and curiosity, reminding us of the intricate dance between the cosmos and our planet. As we conclude this section on the chemistry of light emission in the Aurora Borealis, we invite you to reflect on the beauty and complexity of this natural wonder. Each vibrant color, each mesmerizing movement in the sky is a testament to the intricate processes at play in our atmosphere. The interplay of solar winds, atmospheric gases, and Earth's magnetic field creates a symphony of light that enchants and inspires. In the quiet moments of the night, as you gaze at the sky, may you find peace in the knowledge of the chemistry behind these luminous displays, allowing the serenity of the auroras to envelop you like a warm embrace. As we transition into our next exploration of the factors influencing the intensity of the Aurora Borealis, we will delve deeper into the variables that affect this magnificent phenomenon, understanding the dynamics of solar activity, geomagnetic storms, and seasonal variations will provide further insight into the breathtaking displays that light our polar skies. Each element of this complex system contributes to the beauty we witness. And as we continue our journey, may your mind remain calm and open, ready to absorb the wonders of our natural world. As we continue our soothing exploration of the Aurora Borealis, we turn our attention to another fascinating aspect of this natural wonder, the role of the magnetosphere. The magnetosphere is a region of space surrounding Earth that is dominated by the planet's magnetic field. It plays a crucial role in the formation and visibility of auroras, acting as a protective shield that interacts with solar winds and the charged particles they carry. Understanding the magnetosphere not only enhances our appreciation for the northern lights, but also deepens our comprehension of the dynamic interactions between the Earth and the Sun. The magnetosphere is formed by the movement of molten iron in the outer core of our planet, which generates Earth's magnetic field. This magnetic field extends far into space, creating a protective bubble that deflects most of the solar wind, which is a stream of charged particles emitted by the Sun. However, during periods of heightened solar activity, such as solar flares or coronal mass ejections, the intensity of the solar wind can increase significantly. When this occurs, some of the charged particles can penetrate the magnetosphere, creating a cascade of events that leads to the beautiful displays of the Aurora Borealis. As solar winds collide with the magnetosphere, they can compress it and create a disturbance known as a geomagnetic storm. This storm can cause the magnetic field lines to become more dynamic, allowing charged particles to flow along these lines toward the polar regions of the Earth. As these particles enter the atmosphere, they interact with atmospheric gases, leading to the ionization processes we discussed earlier. This interaction is what ultimately produces the vibrant colors of the auroras, painting the night sky with shades of green, pink, red, and violet. The intensity and frequency of auroral displays are influenced significantly by the strength of the magnetosphere and its interaction with solar activity. During times of strong solar winds, the magnetosphere can become highly energized, resulting in more frequent and intense auroras. Conversely, during periods of low solar activity, the auroras may be less pronounced or even absent. Scientists monitor solar activity closely to understand how these interactions occur and to predict when auroras might be visible. One of the most remarkable features of the magnetosphere is its dynamic nature. It is not a static barrier, but rather a constantly changing environment that responds to the solar wind's intensity and direction. This variability means that the auroras can change in brightness and color, creating a mesmerizing spectacle that can shift and dance across the sky. The interplay of solar particles, magnetic fields, and atmospheric chemistry creates a living tapestry of light that is as beautiful as it is complex. In addition to its role in creating auroras, the magnetosphere also protects life on Earth from harmful solar radiation. Without this magnetic shield, the Earth would be exposed to higher levels of radiation, which could have detrimental effects on our atmosphere and consequently our health. The magnetosphere acts as a guardian, ensuring that the delicate balance of life on our planet is maintained. This protective aspect of the magnetosphere is a reminder of the interconnectedness of all things, how the cosmos influences our existence, and how we, in turn, are part of a larger system. As we reflect on the magnetosphere's influence on the Aurora Borealis, it becomes clear that this phenomenon is not merely an isolated event, but rather a manifestation of the intricate dance between solar winds, magnetic fields, and atmospheric chemistry. Each auroral display is a reminder of the dynamic processes occurring in our universe, a beautiful reminder of how closely tied we are to the cosmos. Now, let's take a moment to appreciate the historical perspectives on the Aurora Borealis. For centuries, the Northern Lights have captured the imagination of humankind. Ancient cultures interpreted these celestial displays through their own lenses, weaving them into their myths and legends. The Inuit people of the Arctic viewed the auroras as the spirits of their ancestors dancing in the sky, while Norse mythology described them as the shimmering armor of the Valkyrie, the warrior maidens who guided fallen heroes to Valhalla. These interpretations reflect the deep connection that people have felt with the auroras throughout history, a connection that continues to inspire awe and wonder today. As scientific understanding of auroras has advanced, so too has our appreciation for their beauty. In the past, people relied on anecdotal accounts and folklore to explain these mysterious lights. However, with the advent of modern technology and research, we have come to understand the chemistry and physics behind the auroras. This journey from myth to science illustrates the evolution of human thought and our quest to comprehend the natural world. In contemporary times, scientists have developed various methods to study and understand the Aurora Borealis better. With the use of satellites and ground-based observatories, researchers can monitor solar activity and its impact on the magnetosphere in real time. This data allows scientists to create models that help predict when and where auroras might occur, enhancing our ability to witness this breathtaking phenomenon. The advancements in technology have opened new doors for exploration, enabling us to appreciate the beauty of the auroras while deepening our understanding of the underlying science. As we consider the modern research and technology surrounding the Aurora Borealis, it is essential to acknowledge the ongoing fascination with this natural wonder. The interplay of science and beauty continues to inspire curiosity and reverence. Each auroral display serves as a reminder of the mysteries that still exist in our cosmos, encouraging us to look up at the night sky and wonder about the universe beyond our reach. In addition to the Northern Lights, there are auroras that occur in other regions of our planet, particularly in the southern hemisphere, known as the Aurora Australis. While the chemistry behind the two phenomena is similar, there are unique characteristics to each. The southern lights, like their northern counterpart, are a result of solar winds interacting with the magnetosphere and atmospheric gases. The beauty of the auroras is not confined to one hemisphere. Instead, it is a global phenomenon that invites all of us to marvel at the wonders of nature. As we draw closer to the conclusion of our calming exploration, it is important to reflect on the science of predicting auroras. With advancements in technology, scientists have developed sophisticated methods to forecast auroral activity. By analyzing data from satellites and ground-based instruments, researchers can track solar winds and geomagnetic activity, providing valuable insights into when and where auroras may be visible. However, predicting auroras is not without its challenges. The complex nature of solar activity means that forecasts can vary in accuracy, and the unpredictable behavior of the sun adds an element of uncertainty to predictions. Despite these challenges, the pursuit of understanding auroras continues to evolve. Researchers are continually refining their models and methods, striving to improve prediction accuracy and enhance our ability to witness these spectacular displays. The ongoing quest for knowledge reflects humanity's desire to connect with the natural world and unlock the mysteries of the universe. As we conclude our exploration of the chemistry behind the Aurora Borealis, we invite you to reflect on the beauty and complexity of this natural phenomenon. The interplay of solar winds, atmospheric gases, and the Earth's magnetic field creates a captivating spectacle that has inspired awe throughout history. The chemistry that gives rise to the Northern Lights serves as a reminder of the intricate connections between the cosmos and our planet. As you prepare to drift into a peaceful slumber, may the beauty of the Aurora Borealis linger in your thoughts. Let it inspire dreams, filled with wonder and tranquility. Take a moment to appreciate the vastness of the universe and the delicate balance of life on Earth. Remember that, like the auroras, we are all part of a larger tapestry, woven together by the forces of nature. Embrace the serenity of the night and allow the magic of the Aurora Borealis to guide you into a restful sleep where dreams of celestial wonders await.